All right, so let's talk about point of inflection. So point of inflection is, as it says, is a point on the graph, on the regional graph. So therefore, can be described with an order pair, that is with your x and y. So here we can describe this inflection point as x and the y, right? Of the form of a of f of a, or f comma f of a. Now, the what makes the point inflection important is the fact that it is the point where the function would change from concavity. That is, that whenever the function changes from concave up to concave down. In a similar argument, we can say that it could be the point where it changes from concave down to concave up, right? So that one point where it changes, that's the point of inflection. And it's actually very easy for us to find once you know the second derivative. Why? Because if you think about it, when you have a concave up, your second derivative is positive. When you have a concave down, your second derivative is less than zero. So here there is a point where it changes from positive to negative, right? Your second derivative changes from positive to negative. So therefore, at some point, in order for you to pass from positive to negative, you have to pass through zero. And that is the point, right? That point is where the second derivative is zero. So we'll talk about that more in the future, but that's pretty much it, right? So it is the point of inflection where the function changes concavity, and that's it, right? We're gonna talk about more in another example, but for now, we'll move on to the second derivative test. The second derivative test is another form or another process that we can use to find local max, local min. That is because, let's say you have a critical number. We know that critical numbers is where you may have a local max or local min. But if we know that critical number happens to be on a concave up, right? Then that means that by logic that needs to be a local min, because it wouldn't make sense, right? If this point happened to be a critical number and it couldn't be um, greater than than zero, right? But also um, it could be that if the second derivative is less than zero, then that means this will be a concave down. In that case, now this will be a local max, right? And that's pretty much the way we're gonna use this test, right? Sometimes it's easier for us to use the second derivative to determine whether it's a local max versus creating the first derivative test where you have to test every single point, right, in between those intervals. So in conclusion, if you have a critical number c, and then when you plug into the second derivative and that gives you an outcome of a negative number, then f is concave down, and so therefore it's concave down, so therefore you have a local max. If you have a second derivative and you plug in c and you have a positive number, that means that you have a concave up, and so therefore your critical number happens in a local min. If your second derivative at c, your critical number is 0, then you can still have a local max or local min, or neither, right? We won't be able to tell, and that would be that means we cannot determine that it's either way, right? So one way we can think about second derivative test is that if you have your second derivative is positive, right? If your second derivative is positive, then you have a happy face, right? If your second derivative is negative, negative meaning like sad, right? Then you have a sad face, right? A concave down. So that's a good way for us to think about it. All right, so this we're gonna try example 3 on the next video.